Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Inshallah, today we'll be discussing a new topic, which is on first derivatives and graph. So let me just open the slides for everyone's view. So So this is basically a continuation on the derivative, where we will basically look into the application, into the usefulness of first derivatives, and in particular with regard to their relationship with graphs. So first derivative, like what we have been dealing so far, like we know that first derivative is associated with the slope of the graph at of a function at a point. So this is the interpretation of the first derivative. Now, besides the slope, first derivative also contained several other information that are related to the properties of a graph. So in this section, basically, we're going to investigate how this information, the information that are derived, that are related to the first derivative, would basically reveal other insights into the shape of the graph of a function. In particular, basically, we're going to look at how to find the absolute maximum and minimum values, which are the valuable information used to guide decision making in manufacturing, in pharmaceuticals, marketing, and many other business areas. Okay, because we are always concerned on how to find the maximum profit, minimum cost. Okay, so we're going to basically try to make use of these absolute maximum and absolute minimum values that are derived from the first derivative, from the slope of the graph of a function. Now, we're going to basically be using sign charts a lot. So please make sure that you still remember how to construct sign charts based on function. Okay. If you don't remember, don't worry, we'll try to basically do an example together. So let's have a look at this example. So we have this function. So what is the derivative? So the derivative of this function, x to the power of 3 minus 3x, will be 3x squared minus 3. Okay, and this, we can factorize this. We can factorize this further because this is a cubic function. So we have x plus 1 and x minus 1. Okay, x plus 1 and x minus 1 multiply with 3. Now, the graph of the function, this function, this is how we draw the graph. So since it is a cubic function, it has this N shape. Okay, and this is how we construct the sign chart. Okay, we construct the sign chart. As you can see here, when we scan the graph from left to right, so we start from negative infinity, the graph is rising. It is going up. When it is going up, our derivative will be positive. The slope of this graph is positive. And that is how we put it here, the slope. So remember, f prime of x, the derivative, this basically is our slope. Since the graph is going up, so we put the positive sign all the way to -1, because when x equals -1, what is the value of our derivative? It is 0. Based on this, we know that f prime of x equals 0 when x equals either -1 or x equals to +1. Okay, so how did we get this from here? When we make f prime of x equals 0, we have these two. Okay, we have these two. So this is where we know that when x equals -1, f prime of x would be 0. Okay, f prime of x would be 0. And then we have our graph, okay, would be going down. Okay, would be going down. So when it is going down, the derivative is negative. So from -1 to 1, the slope is negative. So it is going down. So we put negative sign here. Now, how do we know whether it is going up or down at the moment? At the moment, we simply observe the shape of the graph. Okay, of course, later on, we'll see that there are ways how we can check on whether it is going up or down without the need of drawing the graph. Okay, it will continue to go down until we reach at x equals 1. When x equals 1, again, the slope here is 0. Okay, the slope of f of x is 0. And then the graph will start to rise again. Okay, it will go up. So we have positive from 1, x equals 1 to positive infinity. So please make sure that you remember how to come up with the chart, okay, with the sign chart. Okay. Now, so this basically brings us to theorem 1. So we have one theorem, theorem 1, that basically says that if we have for the interval a and b with these two endpoints, a beginning, b is the end, if f prime is strictly greater than 0, if the slope is positive, then we know f is, the function is increasing, it is going up. If f prime is less than 0, if the slope is negative, then we know the function is decreasing, it is going down. This one is going up and this one is going down. So we can summarize theorem 1 in this table. If f prime of x is positive, we know the function is going up, so the graph of f rises. What are the examples? So these are the examples. As you can see, these are the three examples where the graph, okay, the graph rises. Okay, they are all going up. The function itself is going up, and the slope is positive. Positive slope, and positive slope. While if f prime of x is negative, the function would be decreasing and the graph would be falling. So these are three examples, okay, how a graph with negative slope where the function is decreasing. Okay, how do we find intervals on which a function is increasing or decreasing? So let's say we're going to do this example. So we have this function. Which values, okay, of x correspond to horizontal tangent lines? So what is the meaning of horizontal tangent lines? Horizontal tangent lines, horizon, okay, it is a line like this where the slope is 0. The slope of this line would be 0. So this is a horizontal tangent line. If this is our curve, this is our graph. Okay, if this is our graph. So horizontal tangent line basically means the slope is 0. So we want to find the values of x that correspond to horizontal tangent line. So how do we do this? So first of all, we need to find the derivative and solve for f prime of x equals 0. We're going to make it equal to 0. So what is our f prime of x here? So f prime of x would be, we have 8 minus 2x. And then we make it equal to 0, set to equal it to 0. So we have 2x equals 8, x equals x equals 4. Okay, x equals 4. So what is this? What is this x equals 4? So we know that at x equals 4, when x equals 4, f prime of x is 0. The slope is 0. So we know that a horizontal tangent line exists at one x value when x equals 4. When x equals 4. So more or less, this is when x equals 4. Okay. Now, example 2. Okay. For which values of x is the function increasing, and for which values would the function would be decreasing? We are still dealing with the same function. Okay, with the same function. Now, how do we do this? So basically now we need to, from theorem 1, so this one we need to refer back to theorem 1, which says that increasing happens when the slope is positive, while decreasing happens when the slope is negative. Okay, the slope is negative. So based on our previous answer, so we know this is the slope. So to find which values of x when f of x is increasing, we will basically, okay, oops, let me just check, is there anything? No, everything seems to be good. Okay. So, okay. So where were we? Okay, here. So to find the values of x where the function is increasing, we simply make the slope to be positive, set it to be positive. So we know that whenever x is smaller than 4, okay, smaller than 4, less than 4, then the function would be increasing, okay, increasing. Well, the function would be decreasing when the slope is negative, okay, negative. So we find the slope, we make it less than 0, okay. So be careful when you try to solve for x, because sometimes you may do you may be prone to make a simple calculation mistake, okay, when you change a positive and negative sign. So please be more careful, okay, avoid from making such a simple mistake where you will be losing mark easily, okay. So this one will give us x greater than 4. So f of x, the function would be decreasing whenever x greater than 4. Now, based on this information, so we have already collected, okay, what are the information that we have collected so far? So if this is a straight line, okay, let me just do it here. Okay, let's see. So if we have basically, if this is our x, okay, if this is our x, so we know that this is when x equals 4, we know the slope is 0, isn't it? So let's try to construct our the sign chart. Okay, the sign chart here. So we know that this is when the function, the f prime of x, okay, so if this is a table, so if this is x, okay, and if I have this is f of x, so let's see if we can just somehow try to solve for the simple sign chart based on the information that we have collected from this example. And previously we know that from the previous slide, so what happens when x is less than 4? Our f prime of x, the slope would be positive, isn't it? Positive. And when x greater than 4, we know the slope is negative. Okay, so what happens to our function? So we know our function. So this is basically from negative infinity all the way to 4. And this is from 4 all the way to positive infinity. So our function here would be increasing. Okay. This one would be decreasing. More or less, it will look something like that. So this is already a hint. Okay, so based on this information from part A and part B, you should already be able to guess, okay, how the graph of this function 8x minus x squared would looks like. Okay, so this is how it looks like. So this is 4, right, where this is the partition point that basically separate the graph into two region, two section, increasing and decreasing. And when x is smaller than 4, you can see the slope is positive. The slope is all positive, okay, and then it will become smaller and smaller until it become 0 at the horizontal tangent line. So this is where the slope is 0. The slope f prime of x equals 0. Okay, and when x greater than 4, okay, the slope would be negative. Okay, now this would then we're gonna then define critical numbers. Okay, critical numbers. So what are the critical numbers? So any real number, okay, x in the domain of f such that f prime of x equals 0. So these are the first criteria, or when f prime of x does not exist, okay, is called the critical number of f. So remember, this is how we define the critical number. Okay, critical number. So there are basically two, okay, two types of critical numbers. Okay, so these are basically x when f of x equals 0, or they can also be x when f prime of x does not exist. So these two types of x are what we term as the critical numbers. Okay, the critical numbers. Now, the critical numbers of f that are in the domain of f are partition numbers. Okay, if you remember partition numbers, what are the partition numbers? They are numbers, the values of x that basically separate the graph or the function from increasing, decreasing. When the sign chart, the sign changes. The sign changes from positive to negative or from negative to positive. So that's why they are called the partition numbers, because they separate. They partition the graph or the function. Okay. F prime, the slope, okay, may have partition numbers that do not belong to the domain of f. So they are not the critical numbers of f. Okay. So not all partition numbers are critical numbers. Okay. Only critical numbers that are in the domain of f. Okay. Okay, they have to be in the domain. So when we construct a sign chart, we need all partition numbers of the derivative f prime. We need to know the partition numbers that basically tells us the sign of the slope. Will the slope be positive or negative? Okay. So if f is a polynomial, okay, if f is a polynomial function, then both the partition numbers, okay, for the slope, okay, for the derivative, and the critical numbers of f are the solutions, okay, of f prime of x equals 0. So both the partition numbers, the x, okay, for the f prime that basically partition the derivative, okay, from positive to negative, and the critical numbers of f, okay, would be, okay, the same x would be the solution for f prime of x equals 0, because I mean the derivative, for a derivative to change from positive to negative, you have to basically cross over the value of 0, isn't it? I mean, how come a more or less it's something like that? To make it simple, a number can only change from positive to negative when it crosses 0. So 0 is kind of the partition point, the partition point. Okay, let's try to do this example. So we have this function, a cubic function, fx equals 1 plus x cubed. So we are asked to find the critical numbers of f, the intervals on which the function is increasing, and those, okay, the intervals on which f is decreasing. So there are three things we have been asked to find. So first of all, we need to find the critical numbers, we need to find the partition numbers for the derivative. So we need to find the partition numbers of f prime of x. So what is our f prime of x? It would be, so our f prime of x equals 3x square. Okay, 3x square. Now, and set it to equal to 0. So when we set this to equal to 0, what is the value of x? For f prime of x to be 0, x equals 0. Okay, x equals 0. So what is this x equals 0? So this is the partition number. Partition number. Okay. And since this is the only partition number within the domain of f, so it is also the critical number. The critical number for the function. Okay, so partition number for f of x, and this is the critical number for the function itself. Okay, for the function itself. What is the meaning of this? This means that the slope changes changes its sign from positive to negative or negative to positive. Okay, we haven't investigated that yet, but we know the sign will change here. And at the same time, we know that the slope would be, I mean, the graph would be horizontal. Okay, it will be flat. It will be flat when x equals 0. Okay, so how do we, let's see if we can, now based on this information, can we draw the sign chart? So how do we draw the sign chart? So always, so let's see now, since we already have, let me see, do I have any other space here? So let's try to do it over here. So we have basically divided. So based on this, we know it's from negative infinity to 0, and then 0 to positive infinity. So I'm going to put f of x here. I'm going to put f prime of x here. I'm going to put x here. So if this is x, so we know that 0 is the partition point. Okay, it is a partition point as well as the critical value for f of x. So the slope would be 0. Okay, the slope would be 0. What about f prime of x? When x is negative, when x is less than 0. So when x is less than 0, now focus on this x. If this x, okay, is less than 0, what is the value of f prime of x? It is positive, right? Because negative number, when we take the square value, it will be positive. Okay, positive. And what about when x greater than 0? It is also positive. Okay, positive. Okay, so based on this, we know the graph would be increasing and increasing. Okay, it's just that when it is increasing, there is a one point where the slope is 0. It is not increasing. Okay, it is not increasing. Since the function is continuous, okay, at x equals 0, because this is not a ratio, so we know that the function, okay, it is increasing everywhere. It is going up. Okay, it is going up, increasing non-stop. Okay, so this is a much better sign chart. Okay, sign chart. Okay, where we have the slope here, and we have the function. Okay, here. Okay, another example. Find the critical values of the function, the intervals on which the function is increasing, and the intervals on which the function is decreasing for this. Okay, for this function, where we have 1 minus x to the power of 1 over 3. Now, how do we find the derivative? So f prime of x equals 1 over 3. Put everything back here. So we're going to have negative 2 over 3. And don't forget to multiply with negative 1. Okay, because of we are applying the chain rule here. Okay, the chain rule. So here, basically, we can rewrite everything to make it more elegant. So we're going to have, this is a negative. So I'm going to put 3. I'm going to put all these in the denominator because of the negative power. And I have 1 on top. Okay. Now, if you just take a look here, it seems that the derivative, what is the, um, the value of the derivative? Now, this is um, negative. Okay, this is negative. Um, let's have a look at the denominator. Focus on the denominator. Okay. So the derivative seems to be continuous. This is a ratio function, right? It's a rational function. Okay. So we can say that the derivative, okay, is continuous for all x except, so what is the value that x cannot take? What is the value when the denominator cannot be 0? So remember, denominator cannot be 0. And this, in this case, the denominator would be 0 if x equals 1. So in this case, x cannot equals 1. So what happens when x equals 1? At x equals 1, at x equals 1, What is the value of our f prime of x? It does not exist. And remember, this is the second criteria, the second definition of a critical point, the critical number. Okay, the critical number. So this is, it would be a good candidate. So x equals 1 is the a candidate for the, is a critical number for the function. Okay, for the function. Okay, so since we know that it is basically continuous, so this is the same. It is continuous for all x except when x equals 1, because you give a 0 denominator. Now the numerator is constant, so because it is 1, it is 1, so we just need to focus on the denominator. So since this at x equals 1, f prime of x does not exist, so this is the partition number. The partition number. Okay, the partition number for f prime of x. Okay, because it's separate. This value x equals 1 separate. Okay, separate the function. Okay, the function. So can we somehow try to draw the sign chart? Okay, so this is the sign chart here. Okay, this is the sign chart for this example. Okay, where we know this is when x equals 1. Okay, this is the partition point, the one that we have, because it cannot take the value of 1. Okay, so it is not defined. Okay, not defined. And what is the value of the derivative for x less than 1? Okay, x less than 1, let's take, for example, take 0. So if you replace 0 here, so 0, so this would be 3 multiplied by 1, 1 to the power 2 over 3, and then we have negative. So it is negative. Okay, negative. And what about values of x which is greater than 1? So greater than 1, you can take 2. So this would be negative 1 multiplied with a negative number to the power of 2. So this is a square, right? So whatever number that is square will be positive, and then we have negative. Okay, at the whole function, the whole term will have to be multiplied with negative. So that's why we have negative. Okay, all the way here. Okay, so that's why this function is decreasing everywhere except okay, at x equals 1. Okay, so it is continuous, it is decreasing, decreasing for all x. Okay, decreasing for all x, just that it is not defined. Okay, at x equals 1. Okay. Okay, so just take note that the function can be decreasing or increasing on an interval where its derivative does not exist. Okay, does not exist. So this is the graph of the function 1 minus x to the power of 1 over 3. Okay, so this is where it is not defined. Okay, it is not defined. Where the slope is basically, it is not a horizontal tangent line. Okay, our tangent line is actually vertical. Okay, vertical. And x equals 1 is still our partition number. So it has a vertical tangent. Instead of a horizontal tangent, it has a vertical tangent where the slope is not defined. Slope is not defined here. Okay. So take note of this statement here. A vertical tangent will occur at x equals c, any constant number, okay, any real number. If the function is continuous at x equals c, it is continuous. And if f prime of x become larger and larger as x approaches c, as you can see, the slope here becomes bigger and bigger, isn't it? It becomes steeper and steeper, steeper and steeper. Okay. Another example, okay, partition numbers, okay, for f prime and critical numbers for the function. So this is a ratio. So the function is 1 over x minus 2. So how do we find the derivative? So we simply rewrite this. So how do we rewrite this? This equals x minus 2 to the power of negative 1. So f prime of x would then give us negative 1 x minus 2 to the power of negative 2. So we have negative x minus 2 square 1. Okay. Now to find the partition number, so take note. So how do we find the partition number? So f prime of x, okay, is non-zero for all x, but it is undefined. So undefined when x equals 2, right? When x equals 2, it is undefined. So x equals 2, this is the partition number. Partition number for f prime of x. Okay, f prime of x. Okay. Now, it's just that, take note, now is x equals to within the domain of the function? Is it in the domain of the function? But, so here we have but, x equals to is not in the domain of f of x. Because here, can x equals to? No. Even for the function, okay, the x cannot take the value of 2. And because of that, x equals 2 is not a critical number of f of x. Now, this is different than the previous example. If you see here, now we know that for the derivative, x cannot take the value of 1. Okay, the derivative only for the derivative, but for the because of this, okay, this is the derivative. So for the derivative, x cannot take the value of 1 because the derivative would be undefined. But the function itself is okay. It is defined. I mean, it exists. So that's why it is continuous, because can x take the value of 1? Yeah, no problem at all. I mean, this function, so that's why the value of 1 is still within the domain of the function. Okay, it is within the domain of the function. But here, x equals to is not in the domain of the function, and because of that, it is only the partition number for the derivative, but not, okay, not a critical number of the function. Okay, so no critical number. So this is the graph, okay, of this function here, 1 over x minus 2. Okay, 1 over x minus 2. So you can see the slope is basically, so for all x less than 2, this is square, so whatever value in the denominator would be positive. Okay, it would be positive. Well, since we have a negative sign, okay, so whatever we put here, it will be negative. Okay, it will be negative. Okay, so this is just to these examples are just to basically make it clear to you that certain partition numbers, okay, partition numbers may not necessarily be the critical numbers. Okay, okay, so next would be the local extrema. So when we have a graph of a continuous function that changes from rising to falling, so we have a high point or local maximum occurs, okay, at that point. Okay, so when we have a continuous function, the function is continuous and it changes from going up, and suddenly it goes down. So when it goes down, so basically we have a high point. So that high point is what we call as the local maximum. Okay, local maximum. So the opposite, when the graph changes from falling to rising, so going down, 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 and then the graph start to go up, so we have a low point, okay, or local minimum, okay, local minimum. Now, these are examples of when we have the high points, okay, and low points. So C1, is it will is our does our function? So I mean, first of all, check, okay, all these graph, it is continuous. Okay, it is continuous. So no problem with this function. They are continuous all the way. We don't have to lift our pencil when we draw the graph. What about the, um, I mean the direction? Is it, going down, changes or not? So look at C1. So our graph is going down. It is falling and falling and falling. And after C1, it is still falling. So would this be a high point or a low point? No. So in that case, this is not a local extrema. Okay, not a local extremum. Okay. What about C2? Now before C2 we are falling, and then after C2 we start to rise. So this is a low point or local minimum. What about C3? Before C3 we go up, after C3 we start to go down. So up and down. So this is a local maximum. Okay, local maximum. What about C4? Well, C4 also our graph changes, right? Going down and then we start to go up. So this is a local minimum. What about C5? C5 is not a local extremum because the signs remain. I mean, the graph is still going up. What about this? C6, it is a local maximum. Okay, what about C7? No, because, the graphs continue to fall. Okay, so they are, and take note, okay, take note that they are these points, okay, the high point C3 and C6, okay, and the low point C2 and C4, they are not the highest or lowest of all the points on the graph because we still have, okay, somewhere here and here, so we don't know. So this is not the global maximum. Instead, we call it the local maximum or local minimum because they are only the highest or lowest point for x values that near to them. Okay, when we compare this point to the surrounding neighborhood, they are basically the lowest or the highest in the locality, in that locality. So that's why they are called the local maximum or local minimum. Okay. So this is just to put the definition, the concept in a more elegant way. So function, okay, f the value, okay, fc, okay, is called local maximum if there is an interval, okay, mn containing c, okay, c, any real number such that the function for all other values would be lower than, okay, or equal to f of c for all x in mn. Okay, and the opposite is true for local minimum if f of c is the lowest compared to all other x within this interval mn. Okay, so f of c is called local extremum if it is not either a local maximum or a local minimum. So points on the graph where the local extrema occur are also called the turning points. Okay, the turning points. So these give us theorem 2, local extrema and critical numbers. So if the function at c, okay, function at c is a local extremum of the function f, then c is also a critical number of f. Okay, so local extremum, okay, when we have local extremum, so that means we also, so that the value c, when the function is a local extremum, that value of c is also the critical number. So theorem 2 basically states that a local extremum can only occur only at a critical number. So in order to find whether we are at the local maximum or local minimum, this can only happen when we are at a critical number. But it does not imply that every critical number produces a local extremum. So it's not necessarily the other way around. Not all critical number produces a local extremum. So local extremum, surely local extremum can only happen when C is a critical number, but not all critical numbers would imply that we are having a local extremum. Okay, so to investigate this, to make sure that, okay, so there is a way. So next would be we're gonna basically have this test, okay, for a local minimum. We want to check if we have a critical point, we already know from theorem 2 that a critical point would be a candidate. It's only a candidate for a local extremum. But we need to verify, we need to investigate, because based on theorem 2, not all critical points, okay, would give us the local extremum. Okay, so we need to investigate. So how do we do that? We have the first derivative test. So if the derivative exists on both sides of a critical number C, what is the meaning of this? It means that the slope exists. Okay, the derivative exists on both sides of a critical number C. The sign, okay, of the derivative can be used to determine whether the point C, f of C, is a local maximum, local minimum, or either, or neither. Sorry, or neither. Okay, case one. So we have three cases. When the slope, when the derivative changes from negative, so from negative, what is the meaning of negative, negative to positive, positive, positive? So what is the meaning of this? So what do we have here? So we basically have something that goes down and then it goes up, isn't it? So this one basically means that we are going down, right? The graph is going down and then suddenly it changes to go up. So this means that we have a local minimum here, right? The lowest point, okay? Lowest point, okay? Graphical example. Okay. I mean, maybe I'll just erase my drawing here. Okay. Okay, so here we have when the derivative is negative, we know the graph is decreasing, okay, between this interval. Now C is the critical point that we have already found, okay, and then after C, it seems that the slope or the derivative is going up, okay, so we have a local minimum. So this is our conclusion from case 1, okay. Case 2, okay, case 2, when the derivative changes from positive, 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 positive to negative, negative, negative. So we were like going up and then we go down. So what is this point? It is a local maximum, right? Local maximum. Okay. Now, when the derivative does not change sign at C, okay, it's either positive both sides or negative both sides. So we can conclude that f of C is neither a local maximum nor a local minimum. Okay, it continue to go up. In this case, we cannot establish. Okay, you should take note that, I mean, this is not a local minimum or local maximum, because now this point is higher than this point and this point is lower than this point. So it is not a local maximum and it is also not a local minimum. Okay, so neither local maximum nor minimum at C. Okay, and then case 4, this is when we have the other one. It continue to go down. Okay, continue to go down. So again, we have a case where we don't have a local minimum or a local maximum. So neither local maximum nor local minimum. Okay. Okay, so this would be the first derivative test. Okay, first derivative test. Let's have a look at these horizontal tangents. Why do we need to know horizontal tangents? Because it helps us to identify the location of the critical points. Because we already know that when f, the derivative is 0, so it is a candidate for this, we have a horizontal tangent, right? When the slope is 0. Okay, the slope is 0. So this is just to refresh the definition of the horizontal tangent. Okay, so this would be an example of a horizontal tangent. Okay, so f of c is a local minimum when the sign of the derivative changes from negative to positive. So this critical point, okay, this is where we have a horizontal tangent, and it is a local minimum. Second graph, this is where we have the local maximum when the sign changes from positive to negative, going up and then to go down. Now, in this case, we still have a horizontal tangent, but since the derivative, okay, the sign of the derivative is negative all the way, so we know that f of c is neither a maximum nor a minimum. Okay, and similarly for this example, because it goes up all the way, So this in this case, the horizontal tangent, okay, is neither a maximum nor a minimum. Okay, so these are the four cases that we have discussed before, where we have horizontal tangents. Now, um, remember the third example, okay, when we have the ratio function and stuff. So sometimes for a function, the derivative is not defined. The derivative is not defined, but the function itself is defined. Okay, the function itself is defined. In this case, they can still be local extrema. Now, in this case, can you find the slope of the tangent line? I mean, we can have, we don't have one tangent line here, isn't it? We can have multiple tangent lines here. Okay, multiple tangent line here that only touches this point once. In that case, the derivative is undefined. But the function itself is defined because it is still continuous. It is still continuous here. Okay. Now, and take note that the sign changes. The sign of the derivative changes. Okay, as we approach a c, it's negative, but then it becomes undefined at c, and then the graph start to goes up. Okay, the derivative, the slope is positive. Okay, positive. In this case, f of c is a local minimum. When we compare within this region, okay, um, so this point is the lowest compared to all the other x's. Okay, f of c will be lowest than other f of x. Okay, within that region. And similarly, in this case, this point f of c is higher than all the other remaining f of x. Right? It is the highest within this region. It is the highest. And that's why f of c is a local maximum, even though the derivative is undefined. Okay, undefined. And there are two more cases when we still have undefined tangents, and also they are not local maximum and local minimum. Okay, so this is uh, the for this graph. Okay, we have positive all the way, and the tangent line is not defined here. Okay, it is a vertical tangent line, right? It's a vertical tangent line. So in this case, f of c is neither a local maximum nor a local minimum, because within this neighborhood, local neighborhood, we have the value of x, f of x, which is higher than f of c, and f of x which is lower than f of c. Okay, and similarly here, this is not a local maximum nor a local minimum. Okay, now based on this, basically 8 cases, 8 examples, you should already be able to conclude that, by checking the sign charts, okay, or the sign of the derivative, okay, this sign chart would already be able to basically assist you, help you to establish whether that point is a local minimum or local maximum, or neither. Okay, or neither. I mean, when the sign did not change, then basically that surely that is not a local extremum. Okay, I mean, in this case, the sign changes, right? From negative to positive, from positive to negative. So in this case, we know it is either positive or negative. Okay, positive or negative. I mean, the sign changes. It is either maximum or minimum. Okay. Um. So let's have a look at this example. Okay. So if we have given this, okay, function, we have this function, f of x equals x cubed minus 6x squared plus 9x plus 1. So let's say we need to find the critical numbers, and then we need to locate the local maxima and minima, and then sketch the graph. Okay, sketch the graph. So how do we find the critical numbers? So to find the critical numbers, what we need to do is we have to basically find the derivative, right, for the first one, and then set either equal 0 or do not exist, because these are all the candidates. Okay, so x, so find x, so find x. So the x's that we find, okay, that we found, okay, for under these two situations would be good candidates for the critical numbers. Okay, for the critical numbers. So how do we find the derivative here? So this would give us 3x squared minus 12x plus 9 equals 0. Okay, and this one, it is a quadratic function, isn't it? Okay, so let me just okay, I'm gonna just leave this example to you. I mean, because more or less it's the same one. I mean, we just need to practice, okay, how to basically factorize it. So this is 3. We can take this 3 out. I mean, I'm just want to make it easier by simply using the examples on the slide. So we take this 3 out because it is a common factor. So we have x squared minus 4x plus 3. And we should be able to factorize this further. So this is x minus 1 and x minus 3. Okay. So we know that for x equals, for this f prime of x equals 0 that we have set to equal to 0. So there are two values of x equals 1 and x equals 3. Okay, x equals 1 and x equals 3. So basically f prime of x exists for all x. Okay, the critical numbers are 1 and 3. Okay, for B, okay, for B, the partition numbers. Okay, since we know the partition numbers, okay, give me a minute. I have something I need to um, okay, so partition numbers. So we have two partition numbers, 1 and 3. So now we want to find to investigate whether these 2 points are they local maximum or local minimum or neither. Okay, or neither. So we need to basically draw the sign chart. So the sign chart. So we put here, okay, 1 and 3, isn't it? So we have 1 and 3. So what is and then we take a value. So remember our f, what is our, we did not put it here. So f prime, okay, of x equals 3, x minus 1, x minus 3. Okay, so take a value that is less than 1. If you take a value which is less than 1, what will we have? We will have a, so less than 1 means this would be a negative, this would be negative. So negative multiplied with a negative number, we're going to have positive. So f prime of x would be positive from negative infinity to 1. Okay. And what about from 1 to 3? From 1 to 3, the values of x, which is greater than 1 but less than 3. So 1, this term would be positive, but this term would be negative, isn't it? Because the value would be less than 3. So a negative number, sorry, a positive number multiplied with a negative number would give us negative. So f prime of x would be negative. I mean, if you're not sure, you just substitute a number here. Okay, for between 1 and 3, you can take 2. So 2 minus 1 is 1. 2 minus 3 is negative 1. So 1 multiplied with negative 1 multiplied with 3, we have a negative number. So that's why we have negative. And a number that is greater than 3 all the way to positive infinity. So 3 to positive infinity. So a number that is greater than 3. Of course, this will be positive and this will be positive. So we have positive. Okay. So based on this information, positive, negative, positive. So we know the graph would be increasing. Okay, increasing, going up, and then it starts to go down, and then it starts to go up again. Okay, um, so that's why the sign chart is very, very useful. So based on this information, based on the first derivative test that we have done so far before, since the sign of the derivative changed from positive to negative, so we know that within this neighborhood, x equals 1 would be the highest point, isn't it? So it is a local maximum here. And here we have a local minimum when x equals 3, because the graph will start to, go down before 3, and after 3, it will start to go up. So local minimum. So for part C, we can draw, okay, so this information basically will assist you to be more confident in your drawing. You know that when x equals 1, you have a local maximum, and when x equals 3, you have a local minimum. Okay, take note, these are local, they are not global. Local, just within this neighborhood, because we have other points that would be higher. but within this neighborhood, this would be the highest point and this would be the lowest point. Okay, and then theorem 3. Okay, so this would then theorem 3 basically give us additional information with regard to the intercept and extrema of polynomial functions. Okay, polynomial functions. So if we have a polynomial function, so this is the general form of a polynomial function of the degree n, which is greater than or equal to 1, then the function f has at most nx intercepts. Okay, and at most n minus 1 local extrema. Okay, so there is no guarantee that the nth degree polynomial has exactly n minus 1 local extrema. This is just the maximum number. N minus 1 local extrema is just the maximum number. Like in the previous example, this is to the power of 3, right? Our n is 3. So how many extrema do we have? 3 minus 1 is 2. So this is the most. Okay, it cannot be greater than 2, but it can be less. It can be 1, it can be 0. It can be we don't have any local extrema at all. So that's basically the application of this theorem 3. It helps us, okay, to basically find the critical points and investigate whether they are local minimum or local maximum. Okay, okay. So they can be no more than n minus 1 local extrema. So example 7, I'm gonna leave this to you. Okay, we have done this before, so just go through it. Okay, this is basically a quadratic function. You should be able to take note that we have how many critical points already? I mean, it's already shown here, right? So, so this is the critical points. Okay, the critical points where the sign changes. So all the best and make sure you are familiar with the application, inshallah. So that's all for now. Okay, let me just try to basically yeah, try to end the video and so please go through the examples and also do the questions, because surely we will I will give questions using the first derivative in the final assessment, inshallah. So that's all for today. See you next time, inshallah. Assalamualaikum warahmatullahi wabarakatuh.